Alrighty, hi everybody. Can you guys hear me okay? Yes, no, maybe? Okay, thank you for your confirmation that you can actually hear me. My name is Sydney and I'm excited to be back from being on vacation for a couple weeks, and welcome to the 4th week of the program. Glad to see everyone. Let's get started with lecture number 10. So today I'm excited because it's actually one of my very favorite lectures. We're going to be introducing 2 of 4 very important mechanisms, which is SN1 and SN2. We will be discussing leaving group stability as well as nucleophile stability as well. So the first important mechanism that we're going to talk about is the SN1 reaction. So I'm going to go ahead and draw that on the screen. Let's first pick our alkyl substrate. I'm going to go ahead and ignore stereochemistry for now. So that's why I have more of like what looks like an X versus official wedges and dashes. I'll draw a methyl group. Let's add another methyl group, hydrogen, and we'll pick up bromine. So this is our alkyl substrate. The very first step in an SN1 reaction is we have our leaving group leave the molecule. And in this alkyl substrate, our bromine is going to act as the leaving group. So I'm going to go ahead and draw an arrow showing the bromine leaving the molecule. Try to anyways. I'm going to go ahead and draw our intermediate. I know that you guys have talked about carbocations while I was away. Would anyone like to unmute themselves or share in the chat what type of carbocation we have for this intermediate? Well, this carbon is the central carbon, and it's connected to 2 other different carbon substrates. So this is going to be a secondary carbocation. I'm sorry, this is a secondary carbocation, which is decently stable. Alrighty, so the next step in our SN1 mechanism is we're going to have our nucleophile come over and attack the molecule. So I'm going to go ahead and draw a hydroxide ion. And we have this carbocation with a positive charge, so it's definitely looking for some electrons. And it's going to go right like that. And then lastly, we're going to have our product. Which is very similar to the original substrate, but it has the hydroxide in place of the original bromine. So that's what a substitution reaction does. It substitutes a leaving group with a nucleophile. Are there any questions about anything before we move on? Alrighty, let's go ahead and talk a little bit more about some specifics for the SN1 reaction. The full name is nucleophilic unimolecular substitution. And if we look right here, I know you guys have been talking about rate laws in Chem 2080. This is the rate law for this reaction. Does anyone know by looking at the rate law what order this reaction is? This rate law has one different reactant after the K constant. So this is a first order reaction. There's also kind of a hint in the name unimolecular. So the rate determining step of an SN1 reaction is the formation of the carbocation. So that first step where the leaving group leaves the molecule and you get your carbocation. The faster that occurs, the sooner the rest of the reaction is really able to take place. And it's important to note that SN1 reactions only occur on secondary or tertiary substrates. This is because, if you remember, we're creating that carbocation intermediate, and we want to create an intermediate that's stable. So we're going to want to only have that on secondary or tertiary carbons, or carbocations rather. So that's why I'm going to go ahead and cross out primary and methyl, because you won't generally see SN1 reactions occurring on those substrates because their carbocations would be just way too unstable. Lastly, in regards to stereochemistry, we create a racemized product when we have an SN1 reaction. And I'll explain what I mean by racemized in a minute. Here's an example of the SN1 reaction that I drew a little bit earlier, but this time, because the molecule is chiral, I did go ahead and use wedge dash formation. So just as we did in the last example, we have our sp3 tetrahedral molecule, we've got the bromine leaving, and we get this sp2 hybridized intermediate, which is flat, and it's got the plus charge for the carbocation. This is our nucleophile, a salt molecule. The chlorine ion has a negative charge, so it's ready to attack. And it can attack either from what I like to think of the top of the molecule or the bottom of the molecule. So as a result, you're going to get a mixture of two different products. As you can see here, we have the chlorine on the wedge for one product and the chlorine on the dash for the other. So we're going to get this mixture when it comes to stereochemistry. And now this is actually, lastly, hydride or methyl shifts can occur during SN1 reactions because you have that carbocation intermediate. So this is an example of an SN1 reaction where you might have a hydride and methyl shift. Very important to keep in mind when you're doing practice problems or taking your exam this week. We have this hydrogen, which is on a carbon to the left, and we have this bromine, which is going to be our leaving group, and it's going to be on the carbon that is to the right. So let me go ahead and draw this. The hydrogen on the the carbon that's on the left is a tertiary carbon or tertiary substrate. And the carbon that has the bromine, this one over here that's on the right side, that's a secondary substrate. So when the bromine leaves, you're going to create a secondary carbocation. And we had a secondary carbocation intermediate in another SN1 reaction that we did a little while ago, but those aren't super stable or super ideal. They'll work, but as you can see from up here, a tertiary carbocation is much more stable than a secondary one. So what we can do is we can move this hydrogen over here on over to this carbon that's on the right and create a tertiary carbocation instead of a secondary one, which is much more stable and much more favorable. As you can see here, this hydrogen moved from the carbon on the left to the carbon on the right. And now, instead of having a secondary carbocation, we have a tertiary carbocation, which is good. And we have, again, our nucleophile, which is salt. So I'll go ahead and draw the arrow from the chlorine going all the way over to our tertiary carbocation. And this is going to be our SN1 product, final product, with the chlorine on the carbon that is on the left, because the hydrogen left there and that became the place with the carbocation. And we have our hydrogen, which has moved over. Are there any questions? Alrighty, I'm going to go ahead and check well, not check, but move on to the next slide. So our next mechanism that we're going to be talking about is a little bit similar. It is the SN2 mechanism. I'll go ahead and draw that. Again, I'm not really going to be thinking about stereochemistry too much here, so that's why I'm not using wedge dash formation. I'll add a methyl group, and I'll add a couple of hydrogens, and we'll add bromine as a leaving group again. So in this case, we have our nucleophile, which I'll use hydroxide again, but there's going to be a big difference from our SN1 reaction. Instead of having the bromine just leave at the beginning, we're going to go ahead and just draw an arrow from the nucleophile over to the reaction, or over to the substrate rather. And it's going to do what's called a backside attack, where the nucleophile goes ahead and attacks the molecule from the back. As a result, our bromine is going to be kicked off the molecule because carbon can't have more than 4 bonds. So in one swift step, we have replaced our bromine with our nucleophile, which is hydroxide again. Let me go ahead and draw that. And there we have it. Last time for our SN1 reaction, we had multiple steps. We had an intermediate. There's a possibility for hydride and methyl shifts. Here, we just have one single step where we were able to replace the leaving group with the nucleophile. Bam, here's our product. Any questions about the SN2 reaction? Alrighty, just a reminder for everybody, it's usually easier for the person who's lecturing if you want to direct a question for them if you unmute and ask it out loud versus asking in the chat, just because I just took a look in there and I'm like, oh my goodness, I have some questions, I have some answers. It's easier if you are willing to unmute or post it in the general chat as opposed to direct message. Alrighty, if there are no further questions, I'm going to go ahead and move on and we can talk about some specifics for the SN2 reaction. So just as for SN1, the SN2 reaction has a full name. It's called nucleophilic bimolecular substitution. I'll underline the bi because that's kind of important. We have our rate law posted up here for the SN2 reaction. Would anyone want to share what they think the rate order for an SN2 reaction is? I see somebody post in the chat that it's second order. Thank you. Yes, this is a second order reaction. As you can see here, we have 2 reactants this time in our rate law, both the alkyl and the NU, which stands for nucleophile, if you didn't know. The rate determining step is that interaction between the alkyl substrate and the nucleophile. So basically, when that nucleophile comes in and attacks the molecule and kicks off the leaving group, that's the rate determining step. In terms of stereochemistry, you'll want to keep in mind that SN2 reactions have an inversion of stereochemistry. So again, I have my chiral example and I'm using wedge dash formation. We have our nucleophile doing the backside attack and kicking off the bromine. And as you can see here, the bromine was on the wedge right here, and the chlorine comes and attacks, and now, boom, we have an inversion of stereochemistry. Basically, the molecule has been flipped inside out due to the backside attack, and the hydroxide that was on the dash is now forced to be on the wedge. So basically, if your substrate was S, then your product would be R for an SN2 reaction, or vice versa. And as I mentioned a little bit earlier, SN2 reactions are concerted, so it's just one step, and there's not the opportunity for hydride and methyl shifts. Opposite of the SN1 reaction, the SN2 reaction prefers to have less substituted substrates. This is because it's easier for your nucleophile to do a backside attack on a molecule that has less carbons or other groups on it. So SN2 reactions generally occur on methyl, primary, and sometimes secondary substrates. And as you can see, it's easiest to occur on methyl substituted substrate just because there's the fewest groups. And it doesn't generally occur on tertiary carbons, just because that's considered too bulky, too much steric hindrance for the backside attack to occur. So I'm going to go ahead with my red X, cross that out. Methyl, primary, secondary, those are general rules for what substrates can have an SN2 reaction. Now, I know that this was a lot to go through. Do we have any questions on anything that I have said so far? I'm not seeing anything. So I'm going to assume that there aren't any questions, and we are going to go ahead and move on. So as you might expect, leaving groups are pretty important for these two reactions. Both the SN1 and the SN2 both have leaving groups, stuff that leaves. The best leaving groups are going to be large molecules that are stable with a negative charge. If you remember from watching those different mechanisms that I drew, the group that leaves gains a negative charge after it leaves the molecule in SN1 or is kicked off of the molecule in SN2. So you're going to want something that's stable with a negative charge. Most leaving groups are weak bases. You'll notice that I think almost every single time I picked bromine because it's an example of a weak base. And the bigger the molecule is, the better. A big molecule is also going to be more polarizable, meaning that it can spread charge about itself and keep itself stable with that negative charge that's going to have. So in general, as I've said again, the more stable you are as a leaving group, the better. Now, some leaving groups are not just one single atom. Like you could have a few atoms in a group that acts as the leaving group. And some of the best leaving groups, if it's a group of atoms, have resonance because, as you might remember, resonance increases stability. And resonance is also one way that we discussed that can help you distribute negative charge, which a leaving group will have after it's leaved or kicked off. Leaving group stability, you'll want to keep in mind, is not influenced by a solvent, if there is one. We're not going to talk too much about solvents today, but that's going to be coming up later in the week. And then lastly, something to keep in mind in terms of leaving group is that SN1 reactions especially need a good one. And this is because for SN1 reactions, the leaving group leaving is really a key step in the reaction. If we look back, that's the rate determining step, the formation of that carbocation. So basically, if you don't have a good leaving group for SN1 reactions, the reaction is not really going to be able to take place. This is in comparison to SN2 reactions where the leaving group is forced off the molecule. Are there any questions? Alrighty, let's go ahead. So we've talked about leaving groups, and now is our chance to talk a little bit about nucleophiles, which are also extremely important for these reactions. So the order of best nucleophiles to, I guess, not as great nucleophiles is listed right here. Something you're going to want to keep in mind is that nucleophiles are better nucleophiles or stronger nucleophiles if they are unstable. So we talked about for leaving groups, you want them to be stable with a negative charge. Nucleophiles, you want them to be unstable, because unstable atoms or molecules are more reactive and more likely to attack something. Alrighty. So when we're going through this list of best nucleophiles to worst nucleophiles, the best are going to be what's the most unstable. So starting at the top, our most unstable type of nucleophile or best nucleophile is when we have a negative charge on a less electronegative atom. And when I say more electronegative, that typically includes atoms like oxygen, which you probably remember is very electronegative. When I say less electronegative, I mean an atom such as carbon, which is compared to oxygen, not too electronegative. So a good example for our first type of good nucleophile is CN-. Carbon is not super electronegative. This is a very unstable molecule. Carbon is not happy with that negative charge. It's ready to go and attack another molecule. Next, we have a negative sign on a more electronegative atom. So if you have, for example, hydroxide, which I used several times in our examples today, little bit more stable than carbon with a negative charge, just because oxygen is more electronegative. So there's that. Oxygen is not quite as good a nucleophile as carbon, but still very good. Next, we have a lone pair on a less electronegative atom. So some good examples of this might be SH2. We've got our lone pair on the sulfur right here, or NH3. Both of these are less electronegative than oxygen, which is a good rule of thumb for thinking about atoms that are less electronegative. Compare them to oxygen in terms of electronegativity. And then we have down here, again, a lone pair on a more electronegative atom. So some common examples of this might be water, where we've got that lone pair on the oxygen, or CH3OH. Again, lone pair on the oxygen. Oxygen is more electronegative than nitrogen or sulfur, and thus these two examples are more stable than the ones above, and more stable is less reactive. So these nucleophiles are not as strong as these ones. And then lastly, at the end of our list, we have a double or triple bond. As we've mentioned before in some reactions, those can be a source of electrons that can act as a nucleophile, but it's the less strong on the list, or the least strong on this list. And then another factor that you might want to consider for nucleophile strength is looking at the steric hindrance of the nucleophile. In general, it's harder for a big molecule to move quickly in comparison to a smaller molecule. So this is a molecule called tert butoxide. Samantha's going to talk about it a little bit later in the lecture, but basically it has a lot of steric hindrance. You can see all of the carbon sticking off of it. And so it's not going to be able to move very fast, as you might imagine. This is another molecule that has much fewer substituents. So if I were to compare the strength of these two nucleophiles, I would say that this molecule over here on the right is the better nucleophile, just because there's less steric hindrance and this one can move faster. Lastly, in terms of nucleophiles, SN2 reactions especially need to have a good nucleophile just because they have the backside attack. When you're trying to figure out for comparing nucleophiles, think about for halogen nucleophiles, such as I, Br, Cl. We talked about using them as leaving groups, but they can also act as nucleophiles. The solvent that you have in your reaction for these halogens, that will determine whether a larger halogen or a smaller halogen is better for the reaction. And I'm just saying that in advance for a lecture we're going to have later this week, we'll talk a bit more about solvents and how they impact reactions. So just keep this one in the back of your mind for now, but we'll discuss solvents a little bit later. And then this is just an example of some strong nucleophiles that we have here. And this is an example of some of the poor nucleophiles that we have here. And then just a broad, I guess, just definition of a strong nucleophile versus a weak nucleophile. I know we ranked the nucleophile groups 1 through 5. These 3 down here would be considered weak nucleophiles, and then anything that has a negative charge would be considered a strong nucleophile. So when we say SN2 molecules need a strong nucleophile, you'll want to consider something with a negative charge, like these guys. And then we have SN1 reactions, which can occur with a weaker nucleophile, such as H2O. This is because the formation of the carbocation is the rate determining step. And then after you have the carbocation, a slower moving nucleophile can come and perform the rest of the reaction. You don't need to have a backside attack for SN1 like you would for SN2. Alrighty, I know that was a lot of information. So are there any questions that I can answer about nucleophiles? Alrighty, if there are no further questions, I'll go ahead and pass it over to Sam.
Thank you. Also, if anyone has any questions, just to echo what Sydney said, you can either feel free to unmute yourself and ask them. You can also DM one of our TAs, Sydney, for example, that kind of thing, whatever is easiest for you. Awesome. Can everyone see me scribbling on here?
Yeah, I can see it. You're good, Sam.
Perfect. Thank you. Yeah, as always, let me know if it's buffering a little and I'll slow down. But yeah, let's get started. So you might have noticed that a lot of the qualities for being a good nucleophile are often similar to ones for being a good base. So for example, being unstable with a negative charge, thus wanting to either grab a hydride or grab some other nucleophile. And so nucleophilicity is going to be a kinetic property. When you're thinking about nucleophilicity, you want to be thinking, how quickly can this atom or molecule attack something? And so nucleophilicity, kinetic property, whereas basicity is actually going to be a thermodynamic property. And so for this, you want to be thinking, how stable is this atom or molecule with a negative charge? So for example, a molecule that's stable with a negative charge is less likely to take a hydrogen. And remember that the Bronsted-Lowry definition of a base, let me write this down. Bronsted-Lowry definition of a base is going to be one that accepts hydrogen. So I'm going to say an H+ acceptor. And so as you're soon going to see, some molecules can act as nucleophiles and bases, while some others are just one or the other. Molecules which are only bases aren't generally relevant to the 2 reactions we talked about before, but they're going to be important to the ones we learned on Wednesday, so keep them in the back of your head. Also, just to show you an example of one, you might remember this from the last slide. So this is tert butoxide. Remember, you don't have to draw in these methyl groups. I'll just do it for the sake of showing you. So this is tert butoxide. This is a pretty good base. So this guy's a good base. Not a great nucleophile. So bad or weak nucleophile. Remember, it's for the same reasons that Sydney cited before. There's a lot of methyl groups surrounding this central carbon. It's going to be pretty hard to get in here. There's a lot of steric hindrance. You can imagine if I drew these methyl groups all out instead of just doing CH3, I drew them all out. You can imagine, there's even less room than it looks like when you just draw the methyl group there. It's pretty bulky. Anyway, so to recap, Bronsted-Lowry definition of a base is going to be one that's an H+ acceptor. And thus a weak base is going to be more stable with a negative charge. And if it's stable with a negative charge, it's less likely to want to take up another hydrogen. Awesome. Next up, we're just going to go over some guidelines for nucleophilicity and basicity. And so you're pretty often going to see these problems where you're asked to rank different nucleophiles, usually in terms of strength. You might see that for bases as well. And so here's a quick way to remember that info. Remember, this is only going to apply to non-halides. So not your chlorines, bromines, all that good stuff, because halides are actually going to be subject to solvent effects, which is something we're going to talk about in another lecture, so don't worry about that for now. So first thing is, if two atoms are in the same row of the periodic table, basicity and nucleophilicity are going to follow the same trend. So these graphics also are from Orgo as a Second Language, one of Sydney's favorite books. Am I correct in saying that, Sydney?
Yes,
Talks about that
very
book
highly
all the time.
recommend.
Yeah.
Highly recommend.
Very helpful for this course. If you guys can get your hands on it, I recommend. Anyway, thank you to the textbook for that. And so going back to this, if two atoms are in the same row of the periodic table, basicity and nucleophilicity are going to follow the same trend. So let's say we have nitrogen and oxygen. This versus this. So atoms that are less electronegative. So in this case, nitrogen is going to be the less electronegative one than oxygen. Atoms that are less electronegative, therefore less stable with negative charge or with extra electrons, are going to be both stronger bases and stronger nucleophiles. So this guy is going to be both the stronger base. Let me bring this up. And stronger nucleophile. And then, like I said, we can use this to determine what's the electronegativity difference between these two. Therefore, who's the stronger base and nucleophile? It's going to be H2N minus. So next up, our next trend is going to be that for two atoms in the same column in the periodic table, basicity and nucleophilicity are actually going to follow the opposite trend. So again, let's look at oxygen. Let's do OH minus versus SH minus. And so what tends to be a little bit more relevant here is going to be size. So remember that size is going to increase generally going down the periodic table. Oxygen going to be slightly smaller in size than sulfur. And so sulfur is larger than oxygen, and larger atoms are going to be more stable with negative charges. Therefore, they're going to be weaker bases. So if this is the weaker base, then OH minus must be the stronger base. Remember, follows opposite trends in the same column. So in this case, SH minus is actually going to be the stronger nucleophile. You can also figure this out by looking at electronegativity trends. You can see that the O versus S makes sense. Any questions so far? Let me check the chat. All right, sounds like everyone is good. As always, feel free to let me know. Next up, just a bunch of practice. So first off, it's going to be which leaving group is the best. Remember when we're talking about leaving groups, often we're talking about halides, not always. And what's going to be relevant here, at least for this example, it's going to be size. So remember, size is increasing down the periodic table. Stuff at the top, like fluorine, is going to be the smallest of the column. Stuff at the bottom, iodine is going to be the largest. And so remember, the largest is also going to be the most polarizable. And so based on this, most polarizable also means it's the most stable with a negative charge. If we want a leaving group, the leaving group wants to be stable on its own. That's why it's leaving, right? So iodine is going to be the best leaving group of the three, followed by bromine, followed by fluorine, just based on size. Remember, iodine, biggest, then bromine, then fluorine. Awesome. Next up, now we're ranking nucleophiles. So I know the periodic table is not here, but I'm just going to give you a little handy tip. So sulfur is going to be the most electropositive of the three, then oxygen, then fluorine, which is often cited as the most electronegative atom. A lot of instances, you're not going to see fluorine, especially in like organic chemistry, because it's not something that usually occurs, I think, readily in nature. So a lot of the times, the most electronegative atom you're going to work with is oxygen, but be aware of fluorine just in case they pop that in there for fun. So remember, our order of nucleophilicity is going to go something like this. We're going to have a negative charge on a less electronegative, not of, on, there we go, a less electronegative atom. This is just from Sydney's slide right before. Negative charge on a more electronegative atom, followed by lone pair on a less electronegative atom, and then lone pair on a more electronegative. So remember that in the case of the last two, the thing acting as your nucleophile is going to be uncharged. So generally, those molecules are just going to be uncharged. So let's go ahead and look at our examples up here. So you're going to notice the second one, that's the only one that doesn't have a negative charge. We're going to be using a lone pair there from the nucleophile. And so we can already look at our chart and go, okay, that's probably the worst nucleophile. And so after that, all we're going to look at is nucleophilicity trends. Remember, less electronegative tends to be the best nucleophile. So it's going to be sulfur is the best, oxygen, and then fluorine is the worst of those three. So we're going to go ahead and do 1, 2, 3. Let me put it up here. And so this is an instance where you want to be really careful about how you're making nucleophiles because, you know, SH minus and H2S, they're pretty similar, right? There's only a difference of 1 hydrogen, and because of that, you know, a minus charge. So this is an instance where you want to be really careful about what you're thinking of as the nucleophile. Remember here, it's going to be that lone pair that's attacking. Here, they have that negative charge. Any questions so far? I'm checking the chat and also seeing nothing, so it looks like we are good to go. Cool. So now we're going to go on to some reaction practice. So first up, you're going to see a lot of these questions. So it's going to be some reactant. It's going to be reacting with something. So in this case, NaOH, and then you're going to have to figure out what's the product. Now you guys have been doing a lot of these, so I'm not super worried. What I'd like to do first is look at what we're reacting with, NaOH. And so the relevant part here is going to be the OH minus. What do we know about OH minus? So negative charge is going to be also a strong base. It's also a good nucleophile. Remember, for the reasons we cited before. And so if it's a good nucleophile, this is going to be an SN1 or an SN2 reaction. What do you guys think? Anyone want to throw it out there?
SN2.
Perfect, thank you. I think that was Noah, great job. SN2 reaction. And so remember, SN2 reactions are always going to happen. Let me put this, sorry, we're running out of room, put it up there. SN2 reactions are going to happen on a methyl primary carbon or secondary carbon. Let's look over here. What do we have? So this is going to be the carbon in question. That is a 1, 2 secondary carbon. So we are all good over here. And so remember, when you have an SN2 reaction, what's going to happen first? Let's go ahead and pop off our leaving group. Remember that bromine is going to be a good leaving group. Cindy talked about that earlier. Let me erase this just so I can put in the OH minus. OH minus is going to come in and attack. Let me go ahead and draw this hydrogen in too. You guys know it's there, but. And so we have this Na plus just floating off in space. Remember, he's over there. And so with an SN2 reaction, we're going to get an inversion of stereochemistry. And so that's going to give you a product that looks something like this. My lines are not straight. OH. Do I have the right amount of carbons? Yeah. Hydrogen is now on the wedge. This guy's still up there. And so remember, this is a one-step concerted reaction. So we don't have to worry about methyl shifts, hydride shifts, all that good stuff. You're going to notice if you want to do your R and S, this guy on the left is going to be your S, and the guy on the right is going to be your R. So yeah, that's an example of your inversion stereochemistry. You can draw this guy flipped around 180 degrees if you want. I think that gets a little confusing, but if all else fails, just remember to check for R and S. Any questions so far? All right, let me keep going. Let me know if I'm going too fast and you guys need a minute to write this down. Let's go. Okay, another practice. H2O. Good nucleophile or bad nucleophile? Going to be a pretty bad nucleophile. Sad face. And so this has got to be an SN1, remember? So remember with an SN1, we want to check for methyl shifts, hydride shifts. So what's the carbon here? It's going to be secondary. Let me check 1, 2. Yep. This carbon is also going to be secondary. So we know there are probably no shifts. In this case, it's not going to make a more stable carbocation by shifting things around. So go ahead. Actually, let me draw on the hydrogen. I'm going to pop off this bromine. Let me show you the mechanism real quick. Carbocation. Bromine's just floating out here. Remember that you're going to have water. I'm going to draw it like this. It's going to come, get that carbocation. And the entire water molecule attached. And remember, this is going to undergo the deprotonation step we've talked about in a couple lectures, whereby another water just comes and steals that hydrogen away. And go ahead, leave you with, sorry, I'm running out of room. Let's see if I can put this in here. This. Remember that, and I'm going to go ahead and draw this guy up here. But remember for an SN1 that it's actually going to create a racemic mixture. So it's going to be the product we just formed plus it's an enantiomer. Let me see if I can draw the first one. That was a struggle. Okay. Remember, a racemic mixture is going to be an equal mix, a 1-to-1 ratio of the two enantiomers. Yeah, so hopefully you can tell hydroxide on a wedge, now it's on dash. Same with hydrogen. So let me go ahead and write racemic mixture, which is the two enantiomers. Awesome. Give you another couple seconds to take a picture, write this down, whatever. You're almost there, guys. Cool. Next up, what are the products of this reaction? Same old, same old. Let's look at NaCN. Relevant part here is going to be the CN minus. Hopefully you can already look at it and think, okay, I think that's a pretty good nucleophile. Also going to be SN2. SN2, do we have to worry about methyl hydride shifts? No, remember, it's going to be a concerted reaction. So let's write that down. So it's both concerted, and there's also an inversion of stereochemistry. Version of stereochemistry, remember that's going to be a backside attack. Also concerted, one step. Bromine comes off. CN minus comes in, attacks. Oops. Remember, Na plus just floating out there, Br minus just floating out there. Product's gonna look something like this. Remember the bromine was on a wedge, so go ahead and put your CN on a dash. CN on a dash. I don't think I said that correctly. Anyway, there we go. Hopefully this is starting to get a little bit more straightforward. As you guys do this a lot more, both here and also in the actual class, this will be a lot easier, so don't worry. All right. Last one is going to be this. CH3OH. You may remember Sydney talking about this before, saying it's not a great nucleophile. I'm going to put weak instead of bad. So this is going to be an SN1. And so let's check to see if we would get any methyl hydride shifts. So note this carbon here is going to be 1, 2 secondary. This one here, 1, 2, 3, 4 quaternary. And so hopefully you can tell already that this is a pretty big difference, right? Quaternary and secondary. So we're actually going to get a methyl shift. So let me show you what that looks like. I'm just going to show it as a transition state. So I'm putting in the brackets. It's just an intermediate step. So remember, we originally had that positive charge on the secondary carbocation. Oh, my bad. Let me show chlorine leaving. The chlorine's just floating out here. And so remember, that whole methyl group from the quaternary carbon, one of them is just going to pop over. So like that. And so let's go ahead and show it. Sorry, this is a little janky. Then when we get our, let's move that arrow. We get our CH3OH coming in. It's going to go to that. Now I believe is a tertiary. Yep, tertiary carbocation. Remember, it's more stable than what we would have had. Sorry for the janky arrow. Did I leave myself enough room? Not really. Okay. So remember that one of these is going to, I'm going to go ahead and move this. Sorry, guys. Move that up here. That still relates to that. All right, that's a little bit better. So this is going to have an O, also that H up there, C, H3. So that's just going to be the CH3 in this part, and then the O and the H. Sorry, that's drawn a little weird. Remember, this is still, the oxygen is going to have a plus charge. It's a little bit like when we slap on, water onto a molecule and we hydrate it, and it's still attached to something, still has that plus charge. Same difference. So you can imagine if it is kind of acting like a hydration, just in how you have this cation attached, then you can also dehydrate it. Or sorry, not dehydrate it, but rather deprotonate it. Take off that H. Final product is going to look something like this. Once again, did not leave myself room. Let's see how this looks. And there's going to be a O, C, H3. Let me know if you guys have any questions on that. If not, that is the last slide of the lecture. So you're free to go a little bit early. We'll be here as always for a couple minutes. If you have any questions, you want to go back to another slide, that kind of thing. But yeah. Thank you, everyone. Oh.
Thank you.
Thank you.